The fundamental theorem of line integrals, part 2, independence of path. We're going to start this video with some definitions, an idea, and a theorem. So there's going to be a little bit more of me talking up front, and we'll do a big involved problem at the end. First definition. Suppose that f is a continuous vector field with domain D. We say that the line integral of f dot dr is independent of path if the line integral of f dot dr over C1 equals the line integral of f dot dr over C2. To make this a little bit more concrete, let me give you a scenario. Suppose I have a box on the ground, and I want to pick the box up and put it on top of a shelf. Now I could do it as drawn, but what if I instead had this box and said, well, I'm going to move it to the right first, then up, and then move it back and put it on top of the shelf. Well, first of all, suppose that when I did this, both the first path over here and the second path on the right, it took the exact same amount of work. If that was true, then my line integrals would be independent of path. But now let's pretend a different scenario. Let's pretend on the left, I have somebody who's in the way. He's right there and he's pushing down on the box as I'm trying to lift it up. Now on the right one, the person is there trying to push down the box, except that I go around him and put the box on the shelf. Well, in the second case, that is this right scenario, it might take me less work than it would in the left scenario when somebody's trying to push down on the box as I try to lift it up. In this case, if there's different amount of works or a different amount of work needed, then these line integrals would not be independent of path, because I would get a different value depending on the curve or the path that I took. Now, a quick note. In part 1 of the fundamental theorem of line integrals, we saw that the integral of the gradient dot dr equals the original function at the endpoint minus the original function at the start point, which means the value of this integral depends on the endpoints only, not on the path we take, which shows that the integral over C of gradient of f dot dr is going to be independent of path, always. Quick definition. A curve is closed if r of b equals r of a, that is, its endpoint coincides with its starting point. So a closed curve would be something like this. I start here and I go around and I end up where I started. That's a closed curve. A theorem we're going to state without proof is the following. The line integral over a curve of f dot dr is independent of path on the domain D if and only if the line integral of f dot dr equals 0 for every closed path in the domain. Now, there are an infinite number of paths. So later on, we will find some advanced ways or some other ways to determine if this line integral is independent of path. But let's try to see if this particular line integral is perhaps independent of path. So we're going to look at this line integral, and we're going to do two different paths. Both of them will start at 1, 0 and end up back at 1, 0. So let's do this integral here. Let's start by parameterizing our unit circle in kind of the standard way. R of t equals cosine of ti plus sine tj, which means this is x of t is cosine and then y of t is sine. Then we know that if x of t is cosine, then dx equals the negative sine of t dt, and then dy equals cosine of t dt. Also notice that we're going to be in the time interval, or the t interval, 0 to 2 pi. We're going to go once around the circle. So let's start plugging in. Our integral becomes the integral from 0 to 2 pi of 2x plus 1, so 2 times the cosine of t plus 1, times dx, which is negative sine t dt, plus 3 times y squared, where y is a sine of t, so we have 3 times the sine squared of t, times dy, which is the cosine of t dt. Let's rewrite this before we integrate. So 0 to 2 pi, and then we're going to get negative 2 cosine t sine t minus sine t plus 3 sine squared t cosine t dt. Now we can integrate. I'm going to do some u subs. For the first one, just to show you what I'm thinking, I'll let u equal cosine of t. So if u is cosine of t, du is negative sine t. So this will end up being cosine squared t. The integral of negative sine t is cosine t. And for this back one, I'm doing a separate u sub where I would let u equal sine t. So I would end up with sine cubed of t for the back integral. And then from 0 to 2 pi, so we'll plug in the top limit. Cosine of 2 pi is 1 squared, so 1, plus cosine of 2 pi, 1, plus the sine of 2 pi, so 0, and then minus cosine of 0 squared plus cosine of 0 plus sine of 0. And that equals 0. So let's rewrite this one here, and I'm going to change up my path that I had drawn. Actually, I'll draw it for you here. Let's do the exact same integral. And we'll do the exact same starting point over here. Let's do it 1, 0. And let's do it kind of piecewise like this. So I'm going to start at 1, 0. I'm going to go up, then back to the origin. So up to the point 1, 1, back to the origin, which I'll call C2, and then back to the starting point, which I'll call C3. So I'm going to do the exact same integral, same starting point, same end point, but I'm going to take a different path. And we have to break it down into 3 pieces. So this will take just a little while. So let's look at C1. Notice that for C1, x equals 1 the entire time. And I can let y equal t for t between 0 and 1. Right, so when t equals 0, y equals 0, and t equals 1, y equals 1. And then I can find dx, which is going to be 0, and dy is going to be dt. So now we can plug in up top. We're going to get the integral from 0 to 1 of 2x plus 1, so 3 times dx, well, it's 0, so I don't really need it, plus 3y squared, so 3t squared, times dy, which is dt. So the integral of this will be t cubed from 0 to 1, which equals 1 minus 0, or 1. Now let's look at the second curve, C2, which starts at 1, 1 and goes down to 0, 0. So I could say x equals 1 minus t, and y equals 1 minus t. Certainly y equals x, because that's the actual line, y equals x, on the interval 0 to 1 for t. This is not the only parameterization. You just need to find any one that works. Let's see if it works. When t is 0, both x and y are 1. When t is 1, both x and y are 0. And y equals x, so this looks like a good parameterization. So I can say that dx equals negative dt, and dy equals negative dt as well. So now when we plug in, we're going to get the integral from 0 to 1 of 2x, so 2 times 1 minus t, plus 1, times dx times negative dt, plus 3 times y squared, so 3 times 1 minus t squared, times dy, which is negative dt. Let's simplify this a bit. Integral from 0 to 1 of, let's see, we're going to have 2 minus 2t plus 1, and then times negative 1 dt. So that's going to give us 2t minus 3 dt. And then back here, we're going to get plus, or we'll do the minus here, 3 times 1 minus t squared dt. The minus, of course, comes from that right there. So now if we integrate this one, we're going to get t squared minus 3t, and then plus 1 minus t cubed from 0 to 1. Plugging in the top limit, we get 1 minus 3 plus 0, minus, plug in the lower limit, we get 0 minus 0 plus 1. So we get 1 minus 3 minus 1 equals negative 3. All right, let's look at our final path right here, C3, which is going to start at 0, 0 and go to the point 1, 0. So we could let x equal t, and y is 0, which is going to give us dx equals dt and dy equals 0. So let me rewrite my integral so we can see it over here. We had 2x plus 1 dx plus 3y squared dy. And this will be on the interval 0 to 1 for t as well. So we can integrate 0 to 1 of 2x plus 1, 2t plus 1, times dx, which is dt, and then plus 3y squared, but y is 0, so we don't need to put it, and this is the integral we need on the third part of the curve. So integrating, we get t squared plus t from 0 to 1, which is plug in the top limit, 1 plus 1, minus plug in the bottom limit, 0 equals 2. So if we put these three partial curves together, we get 1 that is my integral, 2x plus 1 dx plus 3y squared dy is going to be 1 plus the second part, negative 3, plus the third part, or over the third partial curve, plus 2 equals 0. So we did two different paths of the same integral, starting at the same point and ending at the same point, and we got the same value. When we went around the unit circle, we got 0. When we went around this triangle here, we got a value of 0 also. Does that mean that this integral is independent of path? Well, no, because we haven't shown every single path, but at least there's a chance that this integral is independent of paths because we got the same value going down different curves.